0. Okay, so the final part of this chapter on complex numbers involves looking at a relatively simple process of proving trigonometric identities. Now, I know it sounds an awful lot more difficult than it actually is when you talk about proving trigonometric identities, but there's one thing that as yet we haven't really mentioned in terms of what a polar form complex number is. And I want you to take a look at this. Notice cos theta plus I sine theta to the power of 3 is nothing more than a binomial expansion. Now, when we're proving trigonometric identities, one of the nice things is that the modulus will always be kept to 1. So the number that's at the outside here will always be 1, just to keep them relatively simple, okay? But it's nothing more than a binomial expansion. Now, we studied how to expand binomials at the beginning of 5th year. We used the binomial expansion theorem to be able to speed up, for want of a better word, multiplying a given binomial, say 2x plus 4y, by itself, say 10 times, okay, or 7 times or 6 times. We can apply that same logic here, which means that not only de Moivre's theorem is the way forward in expanding a polar complex number to a given power, the binomial expansion does the same thing. Now, the only difference is, apart from the procedure used in both, the difference is the form of the answer. Even though the answer will be the same, the form of the answer looks very different, okay? But because both forms of the answers are the same, they can be equated. And on one side, you'll have a real part and an imaginary part. On the other side of the equation, you'll have a real and an imaginary. So what you simply do is you equate the reals and then you equate the imaginaries. And from those two equations will come the identity that you're asked to find, okay? So let's go through this. How do I work out a binomial expansion? For revision purposes, what is a binomial expansion? Well, if you remember, a binomial expansion is any expression containing two terms that is raised to a given power. And what we were told when we were using the binomial expansion is that we use the C function. And the C function is on your calculator just over the division button. So if you want to work out the C function, say 7C4, it's 7 shift division 4. Okay, that's what will do it for you. And I'll demonstrate that here now. So let me just do a little bit of revision in terms of how do I use the binomial expansion with cos theta plus I sine theta raised to the power of 3. The power of 3 is where we kick off as 3C0. Okay, then 3C1, 3C2, and 3C3. Okay, and after those four C functions, you then write each of these terms in their own bracket. So cos theta, I sine theta. Cos theta, I sine theta. Cos theta, I sine theta. Sound like a broken record, but you get the idea. Cos theta, I sine theta. Now, what do I do to them? Well, I've got to assign the powers to both of these parts of the binomial, okay? So we start on the first term, and we give it the cos theta, and we give it 3. And then we decrease the powers on cos theta all the way down to 0. Starting on the sine theta, we start at 0 and move all the way up to 3. And then what we do is we simply work out each term individually, okay? So 3C0, if you're not sure, ask your trusty calculator. All you've got to do is 3 shift division 0 and press equals, and that will tell you what it is. 3C0 happens to be 1, okay? Anything to the power of 0 also happens to be 1. So the answer to that part is 1, the answer to that part is 1, which really means then the only thing I've got to work out is the cos theta to the power of 3. Cos theta to the power of 3, if you remember from your trigonometric chapter, is the same as cos cubed theta, okay? And when we multiply cos cubed theta by 2 1s, it stays the same. So I'm not going to bother writing those down. Okay, next one. 3C1 is 3. Cos theta squared is cos squared theta. And I sine theta to the power of 1 is sine theta I. Now, I would much prefer just to leave the I at the end, so you know then that you're dealing with an imaginary term, okay? Next one, 3C2. Calculator will tell you that 3C2 is 3. Cos theta to the power of 1 is cos theta. Now, be careful with the next step, because both the I and the sine theta have to be squared. So I squared is minus 1, and sine theta squared is sine squared theta. So just to gather these together again, the minus 1 multiplied by the 3 will give me minus 3, leaving me with minus 3 cos theta sine squared theta. Just to do a little bit of tidy up when you're doing these terms. And do the tidy up as you're working on the term. Don't leave it until later on. 3c3 again is 1. Anything to the power of 0 is 1. And that leaves me now with I cubed sine cubed theta. Now, what's I cubed? This brings us back to the start of this chapter. I by I is minus 1, first of all. So if I by I is minus 1, then I by I must be minus 1 times I, which is minus I. So therefore, sine cubed theta I. So to tidy this up then, we get cos cubed theta plus 3 times cos squared theta sine theta I minus 3 times cos theta sine squared theta minus sine cubed theta I. Do you notice anything? Do you notice the alteration between real terms and imaginary terms, and real term and an imaginary term? Now, because it alternates between reals and imaginaries, what I would do next is I would simply gather the reals together after one another. So I would get cos cubed theta minus 3 cos theta sine squared theta, and then I would bring the two imaginary terms together as follows: plus 3 cos squared theta sine theta minus sine cubed theta, and I would put all of them together with an I after them. So just combine them. Makes it just that little bit easier to see what they are. Okay, so the two reals together, cos cubed theta minus 3 times cos theta sine squared theta, that's those two there. So that's the real part of the expression. And then the imaginary part of the expression is 3 cos squared theta sine theta minus sine cubed theta I. And they both there are imaginaries. Okay, so you end up with a real section to your answer and an imaginary section to your answer. Now I've done this in a little bit of a kind of a color-coded way if you want to follow me down here. So the same thing, there's your expansion: 3c0, 3c1, 3c2, 3c3, and so on. That should be 3c3, but it's the same value, it doesn't make any difference. And it gives me the expansion as follows. Okay, your cos cubed theta, which is real, then you've got your imaginary, then your real, and then your imaginary. So what I told you to do when you've got alternating answers like that, just push all the real terms to the front. Look at the blue terms, push them together, and then take the imaginary terms and put them to the end and combine them as 3 cos squared theta sine theta minus sine cubed theta I. So you end up with a real part to your answer and an imaginary part to your answer. All right, so that's what happens when we use what's called the binomial expansion on a polar form number that has a modulus of 1. Okay, now what did de Moivre's theorem tell us to do? Well, de Moivre's theorem told us that if I have my cos theta plus I sine theta to the power of 3, de Moivre says you give the power to the modulus. Well, because the modulus is 1, let's just go through it here. Cos theta plus I sine theta to the power of 3. So we're starting off with exactly the same expression being expanded to the power of 3. De Moivre says you give the power to the modulus. Now, because the modulus is 1, 1 to the power of 3 is still 1. But we don't write it down, all right? And then you multiply both of these thetas by 3. So you end up getting cos 3 theta plus I sine theta. Sine 3 theta. So that is the answer to the expansion thanks to de Moivre. And again, notice you've got a real part and an imaginary part. Now, if that's the expansion thanks to de Moivre, and if I go back a slide, if that is the expansion thanks to the binomial theorem, surely both of those expansions are exactly the same thing. They don't look the same, but they are the same thing. They both have a real part and the imaginary part. And the value of both reals is identical. The value of both imaginaries is identical. So therefore, we can equate them. So what will I do here? So there's the expansion on that one. Let me just remove that for you. And let's just go down this here. So that's what I did a moment ago. You give the power to the modulus, which is 1 cubed, and then you multiply both of these angles by 3, and you end up with a real part and an imaginary part. Now, if I take both sets of answers, the answers I got for both expansions, and I equate them, there's the answer to the expansion thanks to de Moivre, and there is the expansion thanks to the binomial theorem. All right, what do you notice? There's a real part and a real part. There's an imaginary part and an imaginary part. So what we notice straight away is that the cos 3 theta from the left hand side must have exactly the same value as cos cubed theta minus 3 cos theta sine squared theta, because they are both coming from the same starting point under different methods. One is the binomial expansion, one is de Moivre's expansion, but the reals, even though they look different, have to have the same value, and likewise with the imaginaries. So what we do here is we basically equate similar terms. This real one with this real one gives me that equation, and this imaginary with this imaginary gives me that equation. Now you notice that when we're equating the imaginaries, we don't bother with the I. We just write down sine 3 theta is equal to 3 cos squared theta sine theta minus sine cubed theta. Don't bother with the i's. The i's are only there to tell you what's imaginary. You don't have to write the i's down when you're equating them at the end. And guess what? They are two trigonometric identities. That's them. So let's take an example. Let's go on to this one here. Use the theorem of de Moivre to prove the identity sine 4 theta equals 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. Okay, to start this, we've got to take cognizance of the coefficient of the angle at the start of the question. It's 4. So straight away, what I'm going to be doing is I'm going to be taking cos theta and I sine theta and raising it to the power of 4, because 4 theta is required as part of my answer. Okay, 4 theta has to be in there. So what does de Moivre tell us? Well, de Moivre is quite straightforward. De Moivre tells me that to expand this, I give the power to the modulus, which is 1. So that will stay 1 to the power 4, which is 1. And then I multiply both angles by 4. So that gives me cos 4 theta plus I sine 4 theta. And guess what? That's de Moivre's expansion done. That's it. Very simple. Now, we've got to be, I hope I have enough space here, so I'm going to have to write fairly small. In order to use the binomial expansion, we start off with 4c0 followed by cos theta and I sine theta. Now I'm going to have to write this really small. 4c1 cos theta I sine theta, 4c2 cos theta I sine theta, 4c3, I'm going to make it, cos theta I sine theta, and 4c4. So plus 4c4 cos theta sine I sine theta. Not going to do it? Ah, just about. Okay, now unfortunately very small, but you get the idea. Now I've got to assign the powers to these things. So the first term, the cos term, gets the power of 4, then it gets 3, then 2, then 1, then 0. Okay, and the sine term gets 0, then 1, then 2, then 3, and then 4. Now you'll notice, thank God, at the end of this it starts to collapse down a little bit, all right, which is what we need to happen. 4c0 is 1. Anything to the power of 0 is 1. So what does that leave me with? That leaves me just with this term here, which is cos to the power of 4 theta. So that's the first one done. Okay, second one, 4c1 is 4. Cos theta cubed is cos cubed theta. Do you notice? There's the 4 cos cubed theta. See, your answer's beginning to come out here. So that's okay. Just keep your head about you when you're doing these things. And then lastly, we've got sine theta, and then we've got the I at the very end. Okay, so there's your imaginary part. All right. Next one, 4c2. Now, 4c2 is 6. Okay, so 4c2, if you want to see it this way, 4 shift division 2 equals, and it comes out as being 6. So don't take any chances in your head. 4c2 is 6 cos squared theta. Now be careful, because I squared is minus 1, and then you've got sine squared theta in there. Okay, so that comes out as being minus 6 times cos squared theta sine squared theta. So let's just write these down as we do them. So we get plus 4 cos cubed theta sine theta I. And then the next one, minus 6 cos squared theta sine squared theta. Next one, 4c3 is 4. Cos theta to the power of 1 is cos theta. And then I sine theta to the power of 3 is minus I. So that'll be a minus sine theta, and that's I. So we get minus 4 times the cosine of theta, sine of theta I. Okay, and the last term is 4c4, which is 1. Anything power of 0 is 1, and we end up with I to the power of 4. Now I to the power of 4 is the same as minus 1 by minus 1. It's I squared by I squared, which is 1. That gives me then finally just plus sine power of 4 theta. Okay, now what have I ended up with? There's your de Moivre's expansion, and there's your binomial theorem expansion. We have ended up with two answers to the same expansion that look very different, but in essence are exactly the same thing. So we can equate them. See that? We can equate the two answers. There's the answer from de Moivre. There's the answer from the binomial expansion. So we can equate them together. All right. And when I equate them, I simply now know that we've got real terms. That's a real term. That's an imaginary term. That's a real term. That's an imaginary term. And that's a real term. So we've got reals and imaginaries alternating. So what we can do is we've got to look over here and see, what do I want? I want sine 4 theta. Notice that sine 4 theta happens to be part of the imaginary answer on the left hand side. So therefore, let's equate all the imaginaries. Sine 4 theta equals, what's the next imaginary? 4 cos cubed theta sine theta. And what's the next imaginary? Minus 4 cos theta sine cubed theta. Should be cubed in there. And that's it. Now, does that match my answer? Sine 4 theta, yes. 4 cos cubed theta sine theta, yep. And minus 4 cos theta sine cubed theta. That's exactly the answer that we were looking for. So the key thing here is the expansion. Now, the only one that you really have to focus on and be very, very careful with is obviously the binomial expansion, because the binomial expansion does require you to write out every term of the expansion, whereas de Moivre's just applies the formula that you give the power to the modulus and you multiply the answer of the angle of cos and sine by the power that's given. Okay, but if you do that very carefully and you equate the results of both expansions to one another, and then go back and figure out what you're being asked for. You're being asked here to use sine 4 theta, which you see on the left hand side of this equation is part of the imaginary set of outputs or set of answers. Then you're going to equate that imaginary with that imaginary and that imaginary. So you get sine 4 theta equals 4 cos cubed theta sine theta I, yeah, and then minus 4 cos theta sine cubed theta. So you can drop all the i's and just write it down as sine 4 theta equals, as I called it there a moment ago, 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. Okay, pure practice. Not very many of these in the book. In fact, there's only one in the book, and I think that's it. All right, but there's some might be in the exam papers. You might have to take yourself through the exam papers and see how many times they've asked this in the past. Not a lot. It takes a lot of time to do these things, and usually, you know, they do take a bit of time, but usually they would stick down to powers of 2 or 3. They wouldn't ask for a power of 4. It seems to be a little bit too long, but maybe 2s or 3s would be asked in the exam. But I would ask you to go through the papers with the study clicks and pull up what we would call the complex number questions and see if there's any identities in there. If they're not in the complex number questions, try the trigonometry questions and again see if there's any identities they want you to prove there. Okay, let's do one more, and I'm going to leave you with one to do yourselves. Express cos 2 theta in terms of cos theta. Now again, we need to develop a 2 theta. So we're going to start off with cos theta plus I sine theta raised to the power of 2, which is an awful lot more doable. And we're going to expand this two ways, by de Moivre and by the binomial theorem. Okay, so let's do the de Moivre one first because it's easy. That gives me an answer of power to the modulus. Well, the modulus is 1, so 1 squared is still 1, that's fine. And then multiply both thetas by 2. So that's going to give me cos 2 theta plus I sine 2 theta. Okay. Now, let's expand this using the binomial expansion. 2c0, 2c1, 2c2. It's nice and generous, only 3 terms being developed here. Cos theta, I sine theta. Cos theta, I sine theta. And the same thing here, cos theta, I sine theta. And then we just have to distribute the powers over the cos and sine, starting with the first cos, which gets 2, 1, and 0, and the sine terms get 0, 1, and 2. Okay, so now let's take each term separately and work out the answer. Anything to the power, anything C0 is 1. Anything to the power of 0 is 1. So that's 1 times 1 times cos theta squared, which is cos squared theta. Okay, 2c1 is 2. Cos theta to the power of 1 is cos theta. And sine theta to the power of 1, I sine theta to the power of 1 is sine theta by I. Let's put an I at the end. Okay. And then 2c2 is 1. Cos theta to the power of 0 is 1. So this is going to give me now I sine theta squared. The I squared is minus 1. And sine theta squared is sine squared theta. Okay. So when I come back to these and tidy them up, what do I get? Cos squared theta plus 2 cos theta sine theta I, and then minus sine squared theta. And because that is the answer to the de Moivre expansion, that is the answer to the binomial theorem expansion, we can equate them both because it's the same starting point that's being expanded. Now, what do I want? I want cos 2 theta. So that means I'm going to be taking all the reals and looking at them. Okay, so when I equate the reals, I get cos 2 theta equals cos squared theta minus sine squared theta. Now here's the problem. The question says express cos 2 theta, we have it, in terms of cos theta. Yes, no. There's a problem with sine squared theta. But if you remember what we're doing trigonometry, sine squared theta is part of what we call the fundamental identity of trigonometry. In trigonometry, we have an identity that says cos squared theta plus sine squared theta equals 1. That's the fundamental identity in trigonometry. Okay. Now, that means that because I don't want to use sine squared, and you'll find this in your tables, you can rewrite this as sine squared theta equals 1 minus cosine theta. See that? Cos squared. So you just bring the cos squared over the other side, and you end up with sine squared theta equals 1 minus cos squared theta, which now means that instead of using sine squared theta, I can use 1 minus cos squared theta instead. So I now get cos 2 theta equals cos squared theta minus 1 minus cos squared theta. And when I remove the brackets there, cos 2 theta equals cos squared theta minus 1 plus cos squared theta. And to wrap it up, cos 2 theta is equal to minus 1 plus 2 cos squared theta. And that's it. That's the answer. Okay, so again, you're using your tables. Don't forget, this is in your tables. It's the fundamental trigonometric identity. So again, look and see what they're asking to express, because the coefficient of the angle is the power that you're going to have to place over cos theta plus I sine theta. Then, once you've written that, expand it by the Moivre, expand it by the binomial theorem, and set the results of both equal to one another once you've tidied them up. Then equate the reals with the reals or the imaginaries with the imaginaries, depending on what they want you to express. So if the term that they want you to express is part of the real section, then just equate the reals. Your answer should fall out. If the term they're asking you to express is in the imaginary section, just express the imaginaries and the answer should fall out. Okay, I'm going to leave that there, and I'm going to give you one to do yourselves, which is example 3, doing the same thing. Okay, so I want you now to take that expression there, sine 3 theta, and express it in terms of sine theta. Doing exactly the same thing, working with cos theta plus I sine theta raised to the power of 3, expand by the Moivre, expand by the binomial, and then see, can you equate either the reals or the imaginaries to get sine 3 theta in terms of sine theta. Off you go.